Today, January 6th, 2025, marks a peculiar celestial event. Earth reaches its closest point to the Sun, known as perihelion. This event happens once a year, and it's a fascinating reminder of the dynamic nature of our solar system. This might conjure images of scorching heat and blazing sunshine. You might imagine the sun's rays beating down relentlessly, making the days unbearably hot. Yet, step outside in the northern hemisphere, and you'll likely be greeted by a harsh winter chill. Snow blankets the ground, and people bundle up in heavy coats to fend off the cold. How can this be? Why is it so cold when we're practically hugging the sun? This paradox can be quite puzzling at first glance. The answer lies not in distance, but in the elegant mechanics of Earth's celestial dance. Our planet's orbit and axial tilt play crucial roles in this phenomenon. The Sun, our radiant star, doesn't sit statically in space. It moves through the galaxy, and Earth follows an elliptical orbit around it. Earth, in turn, doesn't orbit in a perfect circle. Instead, it follows an elliptical path, which means the distance between Earth and the Sun changes throughout the year. Instead, our planet traces an elliptical path, a slightly elongated circle. This shape causes variations in the distance between Earth and the Sun. Perihelion simply marks the point where we're closest in this cosmic waltz. But proximity alone doesn't dictate our seasonal temperatures. It might seem counterintuitive, but this proximity doesn't translate to sweltering heat. The reason lies in the distribution of sunlight and the angle at which it hits the Earth. The key to understanding this lies in the tilt of our planet. Earth's axial tilt is responsible for the seasons, and during perihelion, the northern hemisphere is tilted away from the Sun, leading to winter. Imagine Earth as a spinning top, slightly off-kilter. This tilt, approximately 23.5 degrees, holds the secret to our seasons. As we orbit the Sun, this tilt causes different hemispheres to receive varying amounts of direct sunlight throughout the year. During perihelion, the northern hemisphere is tilted away from the Sun. This tilt means the Sun's rays strike us at a shallower angle, spreading the same amount of energy over a larger area. The days are shorter and the sunlight weaker. The result? The frigid temperatures we experience in the northern hemisphere during winter, even when we're closer to our star. While the northern hemisphere bundles up in winter coats, the southern hemisphere basks in the warmth of summer. Australia sizzles, South America enjoys long sunny days, and Antarctica experiences its warm season. This stark contrast highlights the profound influence of Earth's tilt. When the northern hemisphere tilts away, the southern hemisphere tilts towards the Sun. This means more direct sunlight, longer days, and increased warmth. So while we're sipping hot cocoa and dreaming of spring, our friends down south are surfing, swimming, and soaking up the sun's rays. Elliptical orbits, a subtle dance of distance. While Earth's tilt is the primary driver of seasons, our elliptical orbit does play a minor role. The difference in distance between perihelion and aphelion, our farthest point from the Sun, is about 3 million miles. This might seem significant, but it results in only a slight variation in solar energy received. During perihelion, we receive about 7% more solar energy than during aphelion. However, this difference is small compared to the impact of Earth's tilt. It's like turning up the thermostat a few degrees noticeable, but not enough to offset the fundamental change in seasons. Solar maximum, a blaze of glory, but little warmth. Adding another layer to this celestial dance is the solar maximum, a period of heightened activity in the Sun's 11-year cycle. During this time, the Sun unleashes more solar flares, coronal mass ejections, and overall energy. We're currently in the midst of a solar maximum, which might lead one to expect scorching temperatures. However, the increase in solar energy during a solar maximum is relatively small, about 0.1%. While this can enhance auroral displays and potentially impact satellites, its influence on Earth's climate is negligible. It's like adding a pinch of spice to a dish. It adds a bit of flavor, but it doesn't change the fundamental recipe. Section 6. Thermal lag Earth's slow seasonal response. There's one final piece to this cosmic puzzle: thermal lag. This phenomenon is crucial in understanding how our planet's climate behaves over time. This refers to the delay between the shortest day of the year, the winter solstice, and the coldest temperatures. The Earth doesn't immediately respond to the increase in daylight. Even though the days start getting longer after the solstice, the Earth continues to cool for several weeks. This is because the accumulated cold from the previous months still affects the environment. This lag occurs because the Earth's surface and atmosphere take time to absorb and release heat. The process is gradual and influenced by various factors like snow cover and cloudiness. It's like heating a pot of water. It takes time for the water to reach boiling point, and it takes time for it to cool down once you turn off the stove. The same principle applies to our planet. This thermal lag explains why January and February are often the coldest months in the Northern Hemisphere, even though the days are getting longer. The Earth's slow response to seasonal changes is a fascinating aspect of our climate system. Section 7. Axial tilt reigns supreme, unraveling the mystery of seasons. So why is it so cold when Earth is closest to the Sun? It seems counterintuitive, doesn't it? One would think that proximity to the Sun would mean warmer temperatures. The answer lies not in proximity, but in the elegant interplay of celestial mechanics. It's a fascinating dance that has been choreographed over billions of years. Earth's tilt, that slight wobble in our spin, is the primary driver of seasons. This tilt, approximately 23.5 degrees, dictates how sunlight is distributed across the planet. It determines the amount of direct sunlight reaching different parts of our planet, creating the seasons we experience. Our elliptical orbit and the solar maximum add subtle nuances to this dance, influencing the intensity and duration of seasons. But they pale in comparison to the profound influence of axial tilt. This tilt is the dominant force shaping our seasonal climate. It's a reminder that even in the vastness of space, the most fundamental forces can have the most profound effects. The tilt of our planet is a perfect example of this. The interplay of these forces creates the beautiful and varied seasons we experience on Earth. So, the next time you're bundled up in winter clothes, feeling the chill in the air, remember that it's not our distance from the Sun that matters most, but the angle at which we receive its light. This angle, dictated by our planet's tilt, is what truly shapes our experience of the seasons.